In this lesson, we're going to look at the inverse of the natural logarithm function, and as we'll soon see, it turns out that the inverse of the natural logarithm is this function e to the x power, where e is a special constant that we're going to define right now. So here's our definition for that number e. So the number e is defined to be the number in which the natural log of e, which is the integral from 1 to e of 1 over t dt, that's our natural log of e, is equal to 1. So it's simply supposed to be the number in which the natural log of that number gives us back 1. Now, the value of e is approximately this quantity, 2.71828182846, and then it just keeps going. It is actually an irrational number. It looks like it might repeat from these first few terms here, but it actually doesn't. It is an irrational number, just like pi. Now, if you look down here, we have a graphical representation for the number e. Right here, the black curve, that's the curve of our natural logarithm function. And then if we draw a horizontal line over from the y-axis, you see it hits the graph right about here. And then if we drop down to the x-axis, right there is our number e. So that's approximately 2.718 right there on the x-axis. Now let's try to understand why this function e to the x power is actually the inverse of the natural logarithm. Now let's notice a few things here. First of all, if x is a rational number, like a over b, remember any rational number can be expressed as the quotient of two integers. So a and b would be two integers. A rational number is also a number in which its decimal expansion either terminates or repeats. And that's the same as saying you can express the number as a quotient of two integers. Then we do know how to define e to the x power. It's simply the bth root of e raised to the a power. So you just define it like this. So we know what e to the x is if x is a rational number. Also note this. The natural log of e to the x, by properties of the natural logarithm, we can just take that x value and drop it right down in front. And we end up with this quantity, but this piece right here is just 1, and so we just end up with x. So we see that the ln of e to the x just gives us back x. That looks sort of like something an inverse function would do. Well, that's exactly what's happening here. Now let's note this. Since f of x equals our natural logarithm function is 1-to-1 on its domain, it does indeed have an inverse function. Let's just call it f inverse of x. And that inverse function will satisfy this. The natural log of the inverse of f of x equals x. Remember, that's just saying that f of f inverse of x equals x. The f in this case is the ln. So that's all we're saying here. And also note that the domain of f inverse is the range of your original function f, and the range of the natural logarithm is negative infinity to infinity. So therefore, we have this fact down here. So the ln of e to the x is x. We've already concluded that for x rational. And the natural log of the inverse function is x as well. And that's true for all real numbers x. So therefore what we have is this. Since the natural log is a 1-to-1 function, we have that these two quantities must be equal to each other. This and this must be equal to each other. We already have discussed the fact that the natural logarithm is 1-to-1, so that means that if I have the ln of a equaling the ln of b, Since the ln is 1 to 1, it passes the horizontal line test. That implies that the a must equal b. So here we have the ln of a, ln of b equaling each other, so a equals b. So what we have now is that e to the x equals our inverse function for the natural logarithm for all rational numbers x. Now let's do this. So therefore we can now extend the definition of e to the x power for all real numbers x like this. We're just going to define e to the x to be the inverse function whenever x is irrational. Recall, we previously defined e to the x when x is a rational number. So if x turns out to be irrational, just define it to be the inverse function. This is defined for all x. So in this manner then we've completely defined the function e to the x power for all x, whether x is rational or irrational, and it is the inverse function then for our natural logarithm. And so since it's the inverse function, it has these two properties down here. So the natural log of e to the x is x, and e to the ln of x is x. You see, this property right here, if we think of f as being the ln function, then this property right here is just stating that f of f inverse of x equals x. And this piece right down here is simply stating that f inverse of f of x equals x. You see, in this case, f of x is ln, and f inverse is the function e to the x. So therefore, we now understand that f of x equals the natural logarithm function, and this function g of x equals e to the x are actually inverse functions of each other, based on what we've just discussed. Now let's take a look at the graph of the ln and compare it to the graph of e to the x. So here we have the graph of e to the x and ln x. Right here we have our graph of the natural logarithm function. And then notice if we flip that graph about the main diagonal, we get the graph of our exponential function e to the x, which is the inverse of the natural logarithm. Notice also that the domain of e to the x is all real numbers from negative infinity to infinity, and that's because the range of the natural logarithm is negative infinity to infinity. So the domain and also notice that the range of e to the x, it only goes from 0 to positive infinity, and it does not include 0. So the range of our exponential function is 0 to infinity, and that's because this is the domain of the natural logarithm function. You'll also notice that e to the x has a horizontal asymptote when y is equal to 0, never actually crosses the x-axis here, and it gets infinitely close to the x-axis, but it never actually touches it. So y equals 0 is a horizontal asymptote, and that's because x equaling 0 is a vertical asymptote for the ln function. So y equals 0 is a horizontal asymptote for e to the x. And once again, that's because x equaling 0 is a vertical asymptote for the ln. Notice if you flip this vertical asymptote here about the line y equals x, it becomes a horizontal asymptote. Also notice the exponential function grows very rapidly as x goes to infinity. And that is because the natural logarithm function grows so slowly. So since the ln grows very slowly as x goes to infinity, e to the x will actually grow very rapidly. And notice one other thing here. Notice that e to the x crosses the y-axis at 1. So e to the 0 equals 1. And that's because the natural logarithm crosses the x-axis at 1. So ln of 1 is equal to 0. So in other words, the point 1, 0 is on the graph of ln, and so 0, 1, which is this point right here, will be on the graph of e to the x. Let's take a look at this quick example before we explore further some properties of this exponential function e to the x. So let's look at this. Let's solve this equation for x. So we have 8 equals e to the 2x plus 1. We just want to solve this equation for x. Well, what we need to do is we need to somehow get this exponential part here out of the exponent. This involves our variable x. We'd like to solve for x. We need to get it out of the exponent. Well, what we can do is take the natural log of both sides. So if I take the ln of both sides, we get this. And now what we can do is just drop this exponent down in front of the ln, and then we'll be able to solve for x. And what we get is and now we know that ln of e is equal to 1. We can just replace this with a 1, so it basically just goes away since we're multiplying by 2x plus 1. If it weren't 1, we could have just divided it to the other side. If this e were something, a number other than e, like 2, we would just divide it to the other side. And then what we can do now is just solving this for x. We get that taking the 1 over to the other side, and then dividing by 2, we get that. Now you can evaluate this on your calculator. Most calculators have an ln button on them, so if you look for the natural logarithm button on your calculator, you'll be able to evaluate the ln of 8. And you get that this is approximately equal to 0.5397. So just verify and make sure that you can evaluate that on your calculator. And so that's the value of x that is a solution to this original equation that we have up here. Now let's take a look at some properties of the exponential function. This is a very important property right here. It turns out, amazingly, that the derivative of e to the x is e to the x itself. So e to the x is actually the only function whose derivative is itself. That's a very interesting property. Let's take a look at the proof of this. So if we start out with y equaling e to the x, we want to prove that the derivative of e to the x is e to the x. Well, let's notice that we want to get that x out of the exponent to do this proof. I'm going to take the natural log of both sides. So if I take the ln of both sides, we get this. Now this side, dropping that x down out of the exponent here, the right-hand side here just becomes x times e times the natural log of e. But this is just 1, of course, and we end up with just x. Now we're going to differentiate both sides. So we get this side, of course, is easy. It's just 1. This side right here, we actually have to apply the chain rule. So here we have to look at this as being d dy of the ln of y times dy dx. See, you can think of this as being like a u in here if you like, and then going d du, ln of u times du dx, but we can just leave the y in place of the u. And so we get this down here. This right here, now since the y here matches with the y that we're differentiating with respect to, this is just going to be 1 over y times, and this is just dy dx, or y prime. And we get that all of this is equal to 1. Multiply the y over to the other side to get it out of the denominator, and we end up with this y prime equals y. Now what this equation tells us, remember y was e to the x, and so this is the same as saying d dx of y, which is e to the x, equals y, which is e to the x, and we have our result. There you go. So this is a nice simple little proof. It's very elegant. We just started with y equals e to the x, took the ln of both sides to get the x out of the exponent. Then we could differentiate with respect to x. Turns out that the d dx of ln y is 1 over y times y prime. d dx of x is 1. Then we just multiply the y over, and we obtain our result. Now let's take a look at this property over here. If u is a differentiable function of x, then d dx of e to the u, well, we just have to apply the chain rule then, so we just write this as d du of e to the u times du dx, and we end up with e to the u times u prime. So that's in case the exponent here doesn't match what you're differentiating with respect to. So if the exponent is a differentiable function of x, you just get e to the u times u prime. That's just a chain rule. So let's take a look at a few examples down here. So let's evaluate the derivative of these functions. First of all, we want to evaluate the derivative of x times e to the x. Well, that's just going to be the product rule, right? So if I have, this is just going to be the product rule. So it's going to be x times the derivative of e to the x plus e to the x times the derivative of x with respect to x. And we end up with this. Notice d dx of e to the x is just e to the x right here. That's this piece right here. And then just d dx of x is just 1. So that's right here aside of the e to the x power. I just didn't write it. Let's take a look at this one. What is the derivative of e to the x squared plus x plus 1? Well, now we just have to apply the chain rule. So we think of this part right here as being a u. And so this is just going to be d du of e to the u times du dx. You see, by writing it like this, the u here match. And so this is just going to be e to the u, that's this piece right here, times du dx, and u is x squared plus x plus 1. So this piece is going to be, and then just substitute what u is into the exponent here, and we get our answer. And there is our answer. You should put parentheses around the 2x plus 1. Make sure you have it written like that. And notice, if you think back to the previous theorem that we looked at, all we did here is we just calculated e to the u times u prime of x. That's exactly what we just calculated right here. This is u, and this is u prime. Let's do one more here like that. So here we want to evaluate the derivative of e to the sine x. Well, once again, we need to think of the sine of x as being the u part. And so this is going to be d du, the u times du dx. And so e to the u. Derivative of sine is cosine. And we get and there's our answer, e to the sine x times cosine x. And let's take a look at one more example before we look at this theorem. Let's find all the inflection points for the function e to the negative x squared. So remember, to find an inflection point, what we have to do is find where the second derivative changes sign. So we're going to have to take the second derivative of this function. So let's notice that f prime so there's our first derivative. This is e to the u. This is u right here. And this piece right here is u prime. E to the u times u prime, that's my derivative. Now I have to take the second derivative. All right, so the second derivative, now I'm going to have to use the product rule. So it's going to be e to the negative x squared times the derivative of negative 2x. So that's going to be plus negative 2x times the derivative of e to the negative x squared. And that's going to be, and there we go. So keep in mind, this is the derivative of e to the negative x squared. Once again, this is u and u prime. Simplifying this, we get, now I'm going to factor out an e to the negative x squared from both of these terms, and we get like that. Now, we want to find where the second derivative is 0 or does not exist. Now, this term right here, e to the negative x squared, that is never equal to 0. The exponential function, if you think back to its graph that we looked at before, it never crosses the x-axis. So this is never 0. So the only part we ever have to worry about equaling 0 is this piece right here. And so we have to set this equal to 0 and solve for x. And solving this for x, we get that. So you just take the 2 over, divide by 4, we get this. And so x is going to be plus or minus 1 over the square root of 2. Now we need to put these 2 points on the number line and use a sign pattern technique with f double prime. So if we put these on the number line, let's make that one the positive one. And over here, now we just have to pick some test points here. For example, if I put 0 in, to the second derivative here, we want to test the sign of the second derivative. If I put 0 in here for x, what we get is e to the 0, 0 in for the x right here, e to the 0, times negative 2. Okay, now that's going to be a negative number. Remember, e to the 0 is 1. So negative in here. Also keep in mind this e to the negative x squared is actually always positive, so really we only need to worry about the sign of this piece right here, since this is always positive. Now let's pick some other test points. I know that 1 is bigger than 1 over root 2. If I put 1 in here for the x's, this is always positive, so I'm going to get e to the negative 1, but that's always positive, don't need to worry about that, times negative 2 plus 4. Well, this is going to be a positive number. And if we put -1 in here, we're also going to get a positive number when we put -1 into the x's for f double prime. And so there you go. Now we have determined that this is where the function has an inflection point, and this one as well. They're both inflection points because we have a change in concavity going across them. So we can say that therefore so those two x values are where the function f of x equals -x squared has an inflection point. And if you actually wanted to label the inflection points on the graph, you would just have to plug those numbers in for x in here, right? So technically speaking, here's one inflection point. And here is another inflection point. You see, if I put 1/√2 in here for x, I get e to the -1/2. So technically these are the actual points of inflection that lie on the graph of the function f. And very quickly, let's just take a look at the graph of this function just to verify that these really do look like inflection points. So here's our graph of the function. Now 1/√2, that's going to be approximately 0.707. And so that's going to be right around right about there. And so that, and if we move over here to -0.707, which would be right around in here, yeah, they do look like inflection points. You see, it does look like we are concave down on this region and then concave up over here and over here. And so it does look like those 2 points are inflection points for this function. Now let's take a look at a theorem and some properties related to this exponential function. First of all, we have a theorem here, and it states that the domain of e to the x is -∞ to infinity, and the range is 0 to infinity. And this is certainly true because the domain of e to the x is the range of the natural logarithm function. And as we saw before, the range of the natural logarithm is -∞ to infinity. So that verifies this one. Also, the range of e to the x would be the domain of the natural logarithm, which is the inverse of e to the x. And so since the domain of ln is 0 to infinity, that's going to be the range of e to the x. Also, the exponential function is continuous, increasing, and 1 to 1. We'll prove that in a second. The graph is concave upward. We'll prove that in a second. And let's note these two first. The limit as x goes to -∞ of e to the x is 0, and the limit as x goes to +∞ of e to the x is +∞. Now these two we can see from the graph of the exponential function, which we had looked at previously. Let's just take a look at that graph again quickly to see why these two hold. So here's the graph of e to the x, this curve right here. And here's the graph of our natural logarithm. So you can see that the exponential function as x goes to -∞, the exponential function e to the x gets infinitely close to the x-axis, so it's approaching 0 right there, but it never actually crosses the x-axis. And that's because the natural logarithm, as x approaches 0 from the right, it goes down to negative infinity. You see, this portion of the graph right here is merely a reflection of the graph of the natural logarithm right here across the x-axis. And so we can see that like that. Also, as x goes to positive infinity, the exponential function e to the x, we can see that that is going to positive infinity as well. So from this portion of the graph, it's easy to see that. And of course, if you just think what the exponential function is, it's the function 2.71828 dot 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 raised to the x power. If x is a large positive number, you're multiplying 2.718 by itself many times, so it's going to be going to infinity as x gets larger and larger, of course. And if x is a negative number, then this is going to be 1 over 2.71828 dot 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 raised to the absolute value x power. That's if x is a negative number, and so you're going to have 1 divided by a very large number, and that's going to be very close to 0. So it's easy to see these two properties here just by considering the graph and what e to the x represents. Now let's take a look at these two properties. E to the x is continuous, increasing, and one-to-one. Well, let's take a look at continuity and increasing. Well, notice that if we take the derivative of e to the x, that is just e to the x. And that is, thinking back to the graph of e to the x, it always lies above the x-axis, so this is always positive for all x. And it exists. So since the derivative of, Now let's take a look at these other two properties. E to the x is continuous, increasing, and one-to-one. Well, to see that it's continuous, notice that the derivative of e to the x equals e to the x, which is positive for all x. Remember, the graph of e to the x lies above the x-axis, so it's positive for all x. And also this exists. So therefore, since the function is differentiable for all x, it is most certainly continuous. Also, it's increasing because the derivative is positive. And it is also one-to-one, because if we let e to the a equal e to the b, then we need to reason that a equals b. Well, if we take the natural log of both sides, this will then imply that but remember, ln e, this is just 1, and this is just 1, and we obtain that a equals b. So therefore, e to the x is one-to-one. And you can easily see that from the graph. If you think back to the graph most certainly passes the horizontal line test. So it is certainly going to be one-to-one. The graph is concave upward. All we need to do is show that the second derivative is positive. Well, the second derivative of e to the x I know that the first derivative of e to the x is e to the x, so the second derivative is going to be the derivative of the first derivative, but that's just e to the x. And I know that this is positive for all x, therefore y equals e to the x is concave upward, because the second derivative is always positive. So those are some important properties of the natural exponential function e to the x. And let's consider these two properties down here as well. These really shouldn't be surprising properties. After all, you've been doing stuff like this for a long time now. X to the a plus b. By properties of exponents, this is x to the a times x to the b. So certainly if the x is the number e, this is still going to hold. And that's what property number 1 says. Now, the only reason we really need to state this as a property here is because technically, you know, that exponential function was defined to be the inverse of the natural logarithm function, but it is a true exponential. So let's prove this result here using the fact that e is the inverse function for the natural logarithm. So to prove this result here, let's just note this. If I consider e to the a plus b, and I take the ln of this quantity, I get just a plus b back, right? And if I take the ln of the right-hand side, well, by properties of the natural logarithm, this is, and then what we can do is just drop these two exponents down, and we get a plus b again. Remember, the ln of e is 1, so that just sort of goes away. And so what we have is that these two quantities here are now equal. So therefore, but the natural logarithm function is 1 to 1, and so this implies that what's in the parentheses will then be equal, because the natural logarithm is 1 to 1 function. And there we go, we've proven property number 1. And property number 2 is certainly true, because e to the a over b is equal to that, and then by property number 1 we can go back in this direction and say that this is equal to e to the a plus negative b, or just e to the a minus b, and we get property number 2. So those are two properties of the exponential function. They shouldn't be surprising at all. And that concludes this video on properties of the exponential function e to the x.